A very good afternoon to you, and welcome to the panel discussion with Nobel Laureates and eminent scientists. We are happy to welcome you today at the Tan Chin Tuan Lecture Theatre. I am Magdalene, and I am from the NTU School of Humanities. I am honored to be the MC for today. This event is organized by the Institute of Advanced Studies at Nanyang Technological University, with support from the Lee Foundation and the National Research Foundation. To begin with, may I now invite on stage Professor Sam Tzu Chien, Director of the Institute of Advanced Studies, to deliver his welcome address. Professor Sam, please.
Thank you. Professor Duncan Haldane, Nobel laureate in physics. Professor Klaus von Klitzing, Nobel laureate in physics. Professor Bertrand, Halperin, Wolf Prize laureate in physics. His Excellency, Dr. Norbert Riedel, German ambassador to Singapore. Professor Panan Tuan, Chair, School of the Physical and Mathematical Sciences. Distinguished guests, colleagues, students, ladies and gentlemen, good afternoon and a very warm welcome to the Institute of Advanced Studies panel discussion with Nobel laureates and eminent scientists. To our guests and international visitors, a very warm welcome to our beautiful green campus. Now today the weather is perfect, not too hot, just nice. But this is an exception, specially catered for you in this symposium, in this dialogue session. Now, it's my pleasure to stand before you as we prepare to delve into the intricacies of emergent behaviors in the quantum world with our three distinguished panel members. I would strongly encourage you, this is a very rare opportunity to try to pick their brains, to dig into all these mysteries of quantum physics. So today's event is made possible by the Lee Foundation and the National Research Foundation Singapore. I would like to thank them for their unwavering support, for the endeavors of NTU IAS and our shared commitment to foster scientific exploration and collaboration. Today's panel's discussion serves as a collaborative event that is linked to the 12th edition of the Global Young Scientists Summit, GYSS, which takes place at the National University of Singapore from 8 to 12 January next week. Now, since its inception in 2013, the GYSS has served as a beacon for aspiring young researchers and esteemed scientific luminaries from around the world. This year marks the 12th summit of this highly successful series, and we are honored to be part of this global initiative that discusses science, technology trends, future game changers, and how research could address major global challenges. Now, the shared objectives between GYSS and NTU-IAS underscore our unified commitment to sparking and nurturing intellectual curiosity among young minds on their quest for knowledge. Now, our collaboration with GYSS has provided invaluable opportunities for engagement, allowing the scientific community to directly interact with distinguished scientists as well as foster knowledge exchange and inspiration. Now, here at IAS NTU, our dedication to scientific excellence spans interdisciplinary studies across science and mathematics, while embracing their applications in materials, electronics, nanotechnology, computing, and engineering. Now, we strive to provide an interactive and dynamic platform for eminent scientists and scholars from diverse backgrounds to inspire future generations and to cultivate leadership in research, discovery, and innovation for the betterment of society. So we are very honored, our esteemed panel, Professor Duncan Haldane, Professor Klaus von Klitzing, and Professor Bertrand Halperin are highly respected and accomplished scientists in the fields of quantum physics and condensed matter physics. So Professor Haldane received the 2016 Nobel Prize in Physics for his work on topological phase transitions and quantum matter. Professor von Klitzing received the 1985 Nobel Prize in Physics for his groundbreaking discovery of the quantum Hall effect. And Professor Halperin received the prestigious Wolf Prize in Physics in 2003 for his profound contributions spanning various aspects of quantum physics and material science. Now, their discoveries have shed new light on the complexities of the quantum world, which when combined with artificial intelligence, promises revolutionary technological advancements. So our esteemed panel offers a rich tapestry of wisdom, diverse experiences, and unparalleled expertise. So it's my sincere aspiration that today's discussion ignites a fervent curiosity within our present students and burgeoning scientists. I envision that this dialogue not only broadens our horizons, but also nurtures an unwavering commitment to lifelong learning. To our distinguished panel members, sponsors, partners, and each one of you in the audience, once again, I extend a warm welcome to NTU. Thank you.
Thank you, Professor Sam. May I now invite our guest of honor, Professor Phan Anh Tuan, Chair of the School of Physical and Mathematical Sciences, on stage to give his opening remarks. Professor Phan, please.
Professor Duncan Haldane, Professor Klaus von Klitzing, Professor Bertrand Halperin, His Excellency Dr. Nobel, distinguished guests, colleagues, students, ladies and gentlemen. A very good afternoon to all of you. It's my pleasure on behalf of NTU to welcome our distinguished guests to participate in today's IAS Lecontian Distinguished Public Panel. Our panel consists of 2 Nobel laureates, 1 Volz Prize winner. Among them, Professor Klaus von Klitzing is the director of the Max Planck Institute for Solid-State Research in Stuttgart, Germany. He discovered the integer quantum Hall effect in 1979, which arguably revolutionized the physics of the 2D condensed matter systems. The von Klitzing constant is now used as the international standard for the units of resistance. Professor Duncan Haldane is currently the Sherman Fairchild University Professor of Physics in Princeton University. For the past 4 decades, he has had a distinguished career in condensed matter physics, making numerous groundbreaking contributions to the theory of the Luttinger liquid, the theory of a one-dimensional spin chain, and more recently, the theory of topological insulator and in particular fractional quantum Hall effect. Professor Bertrand Halperin is the Hollis Professor of Mathematics and Natural Philosophy at Harvard University. Throughout his career, he has made a number of critical contributions in the theory of quantum fluid and solid in low dimension. This includes the prediction of the hexatic phase in the melting of 2D solids, the study of quantum Hall effect, and a number of pioneering works on the role of topology in both classical and quantum systems. It is also my great pleasure to introduce Professor Antonio Castro Neto from the National University of Singapore, who is here to join us as the moderator of the panel discussion. Antonio is the director of the Center for Advanced 2D Materials and distinguished professor at the Department of Physics at NUS. He has made important contributions in the studies of electronic property of graphene, superconductivity, strain engineering, and twistronics. We are thrilled to have an amazing collection of minds gathered here at the beginning of the new year to share with us their thought on some of the most interesting physics research they have encountered in their careers. The real world is complex, with rich phenomena from the interplay of many different components arising from the law of physics that themselves simple and elegant. To understand how complex behavior emerges from the interaction between many simple objects is one of the core scientific pursuits of the modern age. We look forward to a timely discussion to explore the implication of the emergent physics in this quantum age, in particular where our society is facing paradigm shift brought by recent development in quantum computation and artificial intelligence. I believe all of you will leave today the panel discussion inspired by our panelists and fascinated by delicacy and richness of our physical world. In closing, I would like to thank the Lee Foundation for its support and the Institute of Advanced Studies for organizing this event. I would like to convey my gratitude to our distinguished panelists, and thank you.
Thank you, Professor Fan. Now, let's get started with the panel discussion. Please note that there are 2 standing microphones available at each side of the lecture theatre for any questions. I would now like to invite Professor Antonio Castro Neto to be the moderator for today's panel discussion. Professor, please.
All right, I'm honored to be here today to be the moderator of this panel for several reasons. So the 3 scientists who are here with us today, they had a huge influence in my life and many things I've done over the years, and a big fan of all of them. So I'm very happy to have them here today. So I think that I was told that this is a very broad audience, that some people here may not even know what quantum mechanics is about. So I will try to keep the discussion at at the most basic level so everybody can follow what's going on, right? And we're talking about quantum world. So what's the quantum world? So, and people say that we live in the quantum age. And why we're saying that? So these 3 gentlemen, they have spent their career doing quantum physics. So they live in the quantum world for a very long time. And I want to, understand where their minds are in terms of the future, in terms of this quantum age. Okay, so I think this sets the stage for what we're going to talk about. Thank you. Oh, we all sit there? Okay. Okay, so to break the ice, I want to ask the 3 of them about what's exciting in science for you right now, and what's making your brain tick? What are the problems that you think are fundamental in quantum mechanics these days? So maybe Professor von Klitzing, you start.
Okay, sure. We'll start with quantum. In 25, we will have a world year of quantum science and technology. The United Nations, UNESCO, will declare this, that in 25, we have this world year. So this indicates already that this is something very, very interesting to the public. Like in 2005, we had the Einstein year, and in principle, Einstein year was already a starting point to go to the public, to bring to the public this complicated system. But for me, I'm director at the Max Planck Institute, and sure, I have to make public relations for Max Planck, because he was in 1900 the person who started quantum theory, even if he didn't recognize that he discovered quantum theory, just explaining nature. We have always tried to explain nature, to understand nature, and then we have to introduce some theories, and the quantum theory was necessary. And I worked all my time connected to quantum theory. At my study 60 years ago, I thought, okay, these are just mathematical problems, but today we can really use quantum physics for practical application. And you know, everywhere in the world, all our illumination, the lightning, all the computer technology is based on quantum physics. So we used always quantum physics in the past. We called nanoscience technology. This was always connected to quantum physics. If you go to atomic dimensions, then everything is quantum physics. But now the motto of this world year of quantum science technology will be 100 years of quantum physics, just the beginning. This indicates that a lot of people believe now we have a starting point of a new area. We can apply some ideas of quantum physics in a new direction, and we will speak about quantum computation. This is one of the words. We will have some discussion about this, I am sure. But this is in the public, artificial intelligence, quantum communication, okay, and our energy problem. These are the most interesting topics also in science now. And as a Nobel laureate, we are very often confronted also with problems which are not directly connected with our daily work. So global warming, all these things. And okay, solar energy is quantum physics, is pure quantum physics, yes? So these are my problems, so I'm engaged a little bit in this question also, which combines quantum physics with really the problems of what happens in the future. Okay, that's the first.
Thank you. Professor Haldane.
Yeah, well, after 100 years of quantum mechanics, it seemed like it was a well-worn subject, but in recent years, we've entered what people have been calling probably the second quantum revolution. In a sense, our way of thinking about quantum mechanics has changed somewhat. There was an idea of, in fact, Einstein was great, although he got his Nobel Prize for one of the second parts of quantum mechanics discoveries, he kind of rejected it in his later life. And he came up with this notion of quantum entanglement, which he thought was a property that quantum mechanics predicted, which was too strange to be true. So he always thought that this would be tested experimentally and the quantum mechanics was found to be wrong. But this was always a very abstract kind of philosophical thing until experiments started to be done. And in fact, the recent Nobel Prize was indeed for the work that showed that Einstein's strange quantum mechanical property was really true. And this has started to become viewed as the principle, the fundamental part of quantum mechanics is now not so much the uncertainty principle that everyone kind of vaguely knew about in the past, but the entanglement issue of quantum entanglement. And our way of thinking, people started thinking in quantum mechanics on a rather different way and trying to test entanglement and see if they can find a way to use entanglement for, the dream is for quantum information processing, and most of the exciting work today is trying to find real physical systems in which interesting issues of entanglement are present. You can, on paper at least, you can hide quantum information in a way that's invisible to local perturbations. And there's lots of, so this is a rather new way of thinking about quantum mechanics has really caught hold, and that's why people really are talking about the second quantum revolution.
Thank you very much. Professor Halperin.
Is this working? Yes.
Yeah.
I don't have a single direction that I think quantum mechanics is most exciting about or is going to go. For me, quantum mechanics is very broad. It is a language that we have to learn to understand so much of the phenomena that happen in the real world, from the fact that there are atoms, to the fact that we don't collapse into nothing because the attraction between the electrons and the protons, if it weren't for quantum mechanics, everything would just collapse and we wouldn't be here. So everything in chemistry depends on quantum mechanics at a microscopic scale. As Einstein would have said, it's an almost unbelievable theory. It's just so elegant to learn it and to understand how you can apply it to things. And for me, my excitement, I have to admit, it's wonderful when I can think of something that has some application. But for me, it's just learning how it manifests itself in so many different ways, and you get so many surprise. Every once in a while, there's some tremendously surprising things that come out that you would have thought you understood what quantum mechanics predicts, and then all of a sudden, there's some new phenomenon. The quantum Hall effect was one of them, the most dramatic, but a lot of smaller things that happen, and things maybe that you even can, if you're doing quantum mechanics, maybe you can explain some experiment that seemed absolutely mysterious, and some of the things that I found most exciting were not necessarily the most important things, but when you could explain something that seems so mysterious and suddenly it comes about. How these things are applied to things, well, obviously, as you said, if we're interested in solar energy conversion, that's a quantum mechanical process, and you want to optimize that quantum mechanical process, you have to know quantum mechanics in order to be able to think about it. So there are many engineering problems, more and more as time goes on, for which quantum mechanics becomes important, and we should learn how to use it, and the better we are at using it, the more we can solve some of these problems. Of course, there are lots of other problems in the world that quantum mechanics is not going to help us with, let's face it. There's social problems, and I'm not sure that would be, if you, the excitement of quantum mechanics is maybe partly that because it has applications, but partly because it is so beautiful. And I liked one of the things that Professor Sung said in his introduction. At the very end of his talk, he spoke about one of the virtues of this Institute for Advanced Studies. It's to encourage lifelong learning. Well, I've been in the field now for quite a few years, and I keep learning. And I would, again, for the young people here who are thinking about their future and what they want to do, they have to think about what they're going to do next year and the next 10 years and what the particular project is. But I think you should always think that the goal of what you do is lifelong learning, not just for yourself, but we could say for the world in terms of learning about what quantum mechanics can do. So that's sort of my attitude towards it.
Thank you very much. So I want to go back to the issue of the second quantum revolution, because I think there is a huge focus on quantum information these days, and it's at least I sense that even the universities and the education about quantum mechanics is changing. So when I was a student, it was all about understanding materials, for instance. Now people are being educated in terms of qubits, right? So we're just talking about two-level systems and how they are applied in quantum information. So I want to get a sense from you, is the teaching of quantum mechanics going to change? Is the formation, the way people are educated is changing because of this sort of second quantum revolution? Maybe you have.
Yeah, I would say things have completely changed since I was a student. Yeah, I mean, the amazing thing, the amazing thing in what's happened in quantum mechanics is so many surprising developments have happened experimentally or otherwise. So quantum mechanics has turned out to permit things to happen that people didn't dream could happen. So all kinds of, it's more remarkable than people thought it was. And these discoveries often combined with big improvements in materials development taking place, but a large part of it has been being able to construct the theorist's toy models, the qubits, to realize that you can assemble, rather than stick with what nature gave you, you can actually try to build things and demonstrate some of the surprising principles that have emerged. And really, they've been big surprises. For example, what Klaus discovered, the quantum Hall effect, was something no one would have dreamt of until they actually saw this thing emerging before their eyes in the laboratory. And so our way of thinking has been changed tremendously by when I learned quantum mechanics, it was rather cut and dried, and people thought we kind of knew all the basics, and suddenly new stuff came along that showed us that we were being overly confident about knowing the basics, and showed us there was much more exciting stuff out there to be found. And the pace has actually grown because more and more people have been looking at exotic materials and pointed in this direction, and surprising discoveries, including stuff coming out of graphene, the so-called twisted graphene, Antonio mentioned. All kinds of surprising things have happened. Even this year, since 6 months ago, we've discovered something called fractional Chern insulator, with obviously a very abstract kind of technical term, but something rather remarkable that people hadn't dreamt of, and people are hoping, again, that some of these developments will play a role for some of these information technologies.
Okay, but there's not really something very new. In principle, all this knowledge about quantum physics exists already for a long time, but we are now able to control many nano devices to demonstrate that this works really. So really, when I was a student, I thought particle in a box, it will fall down, an electron, and okay, then we learned there's a wave behavior, and I thought, okay, this is a nice exercise. But today, in material science, we can really control at atomic level layers, we can make artificial materials. If you look at the last Nobel Prize for quantum dots, for example, the small particles, depending on the size of the particle, you get different colors out of these particles, and we can control all these parameters today. So this is very normal. Only the entanglement, if we can demonstrate that they are useful, then it will open a new parameter. But it's not a new physics. In principle, it's covered already in the curriculum. I don't think that the university has to change. It's covered already, but we have to point out that now we can transform this perhaps in some application. And the engineering point in many fields will be very, very important. The basis, the physics basis, is known for a long time. And you asked about the future quantum. So it was mentioned that I just added quantum to the old-fashioned Hall effect, which is 150 years old. And for me, this was the most excited moment when I saw that about 40 years after my discovery, there was a big application in quantum metrology. This is, if you measure something, we have to know our so-called base units. So if we measure something, we know exactly the kilogram, meter, second is the most important base units. They have to be very stable. And now, if we speak about quantum, that we have now a new definition of the kilogram, perhaps it's not known to the public too much, that the kilogram today is defined by the Planck constant. This is quantum physics. So the Planck constant is a formula, the basis for a new definition of our kilogram. So I think the majority, which are not in science, they believe in Paris we have still metallic block, which is a kilogram. No, that's not true. And this was in 2019, on the 20th of May 2019, all governments in the world changed the laws for our units. So we have changed the kilogram, we have changed the Kelvin, the temperature scale. It's not the melting of ice, it's not the fixed point. And quantum metrology started this revolution. And fortunately, the quantum Hall effect started also to have this revolution. And this was for me the highlight in my life. I was invited to Paris where they have this kilogram and the second, and I convinced the delegation of all over the world that the quantum metrology, where we have a new definition of the current. What is the current? Formerly it was the force between wires, very complicated. Current is that electrons are flowing. And today we can count the electrons which are flowing per second. This is electrical current. And then the idea came up that we have fundamental constants. These are stable. Constants are stable. And it was mentioned from Klitzing constant. By accident, I discovered this constant, which is always the same everywhere in the world. You can measure with 10 digits this quantity if you do an experiment. And this is very stable quantities, and therefore the idea came up to use fundamental constants for our measurement system. And today we have fixed values for fundamental constants to have a stable international agreement for this unit. And it was really fantastic to see that all countries in the world, even the Americans, the Russians, the Chinese, and in Europe, even the Turkey and Hungary, all of them agreed to have this new introduction. So the science was the binding property between the different countries. And I think this will never happen in the near future, that all these countries will agree on something. And this was for me really the highlight of this. But if you come now to quantum computation, I give also a warning point. We have now something like Manhattan Project in quantum computation. Last year, we spent worldwide in quantum technology $30 billion. And about half of the money is spent in China. And now is a competition mainly between China and the United States. We have a science war already in this field. And I see this as a negative point of the development. We are still far away from really using the quantum computer. I'm skeptical that we will have this in 20 years' time. And it's still basic science, and basic science is for international cooperation and not for a conflict between the countries. So this is quite different from quantum metrology, where all the world agreed with, because we need everywhere in the world the same units to have international exchange. But in the quantum computation, because in '94 there was some theoretical development that you can crack a security code which is used today for all the bank transfers and so, the so-called Shor algorithm. And then in about 2018, all over the world, we started with quantum programs. And in Europe, we have this flagship, quantum flagship. In the United States in 2018 was a national activity about quantum science. And last year, Biden made the proclamation, the United States has to be the leading country in quantum computation. And then this is really fighting, and this is not natural, and this is dangerous for science, for international cooperation. So my message is there's so many fundamental questions in this. And we have today, also in quantum physics, possibilities to have a secure information transformation, the quantum internet. There's so many open questions that one has to solve this together and not against each other. So this is my negative contribution. Everyone is happy if a lot of money is spent for science, but one should be careful not to oversell something. And I am skeptical. I know the situation about the qubits, how difficult it is to keep these qubits stable. And this extrapolation to a large number of qubits, we need some new ideas. And perhaps topology, which is one of our fields also, may give a new quality also in this field. But the present situation, we have these quantum computers from IBM all over the world, but they reduced already the roadmap for next year. They promised 4,000 quantum bits, but they go down now. They say the quality is not good enough of the quantum, and there's a lot of basic sciences necessary to improve the quality of these qubits. So it works from the scientific point of view, but then the transformation in the big application, I think it will need a long, long time, and we should not fight against each other, but cooperate in this field.
You're right. So Professor Halperin, please.
Thank you. Well, first, I agree with basically what Professor Klitzing said, and we could return to that theme again, but I'd like to go back to the original question you asked, which was about the to what extent has the instruction, or the way we would teach quantum mechanics changed? And I think with this, I kind of disagree with what Professor Haldane said. I think the basic mathematics, the basic principles of quantum mechanics that you would teach today, and I'm actually retired from teaching, so I haven't taught quantum mechanics for a number of years, but I think the basic principles are the same as when I learned them 150 years, well, I mean, some number of years ago. Not quite 150, I have to admit, but quite a few years ago, a good deal more than 50. And you have to teach the ideas of Hilbert space. You have to teach the ideas of what's called Hilbert space, of vector space. There are mathematical ideas. There's the ideas of wave functions and density matrices, and these are all mathematical ideas. Collapse of wave functions, the extent it's correct and not correct, and all of those ideas were things that I was certainly taught either in my, not necessarily in the first year, but in the very first years. The order of things that you would teach might be different. The focus on discrete levels rather than continuum levels, I think it would make more sense now, because that it has much more useful applications at the very beginning. And the illustrations, of course, are different. So now, when you want to talk about particle in a box, simple model, you can talk about quantum dots and how this is actually useful, because you have dots of different colors. So there are a lot of examples that didn't exist before. If you're teaching about, this is not necessarily first year quantum mechanics, but you go a little beyond that and you start talking about elementary band structure of periodic systems. Now you can talk about graphing. You can talk about a two-dimensional system, which is much simpler than not as. First you talk about one dimension, then you talk about 2 dimensions, which is still simpler than 3 dimensions, but it also has fascinating things. And now you can say, well, here's where it's really applied, and that of course makes it more exciting. But the ideas, I think, are really, the basic ideas are the same. There are a lot of new ideas that you need to learn, and particularly a lot of the examples we talked about are many-body examples where you have many particles interacting. Okay, that's emergent quantum mechanics already, and that you have to teach, but you sort of have to learn the simpler stuff first.
Yeah, so I want to go back to this, because I think that, for instance, for quantum information, the focus is more on the time dynamics or on time evolution than on, say, equilibrium properties, right? So I think that the traditional books focus a lot on the equilibrium part, right? So, but for people who do work with entanglement and things like that, they are always thinking about what happens if I act on a certain state at a certain time and how it evolves in time. And I at least I don't know, maybe you know more than I do about that. You know, most books do not focus a lot on that, and that's, I think it's a new way to teach quantum mechanics, right? So, but I want to go back to the issue of the importance that this, for instance, quantum information and quantum computation will have for the world. So what sort of impact you see in the world because of the evolution in these areas? For instance, can you envision, say, a robot who has a CPU made of a quantum computer walking around and doing things, right? So I want to try your imagination. So what do you think is out there? If you imagine, you can imagine anything, but within the rules of quantum mechanics, where does your imagination take you?
Well, we don't really know exactly what the quantum computers will do for us. And fitting them in a robot is a bit ahead of its time. I think we're really in the middle of exploring what exactly, on the one hand, people are trying to find out what exactly a quantum computer can do. That, I mean, the original idea was quantum computers, according to Feynman, was a method of calculating quantum mechanics problems, right? But for designing materials or getting a better understanding, breaking codes is kind of a new kind of thing that came up in the 90s with the Shor algorithm. But yeah, what they will actually do, people will really emerge when and if they're built, right? And people are building assemblies of qubits, and they do seem to be getting better and better. I mean, you're fighting this exponential problem of decoherence, which one hopes things like topological quantum protection might one day help, but so far it hasn't been successful. But yeah, the developments will come as what people can do with it will depend on which ones are built and how they work and if they work. Yeah.
Okay, there are different levels. So the quantum computation is far away, and I'm sure, you should never be sure, there may be, but I will not have in 10 years' time a quantum computer at home. And a quantum computer will never replace our standard computer. This is not, I heard different governments say, okay, now we want to follow the success story of the normal computer. This will not be the case. We will have always combination of the supercomputers or classical computers with quantum computers. And I heard there's a lot of problems to feed in a quantum computer. You need already a supercomputer to have this interface to a quantum computer. So quantum simulation, I think from the scientific point of view, this is realistic. There will be problems to be solved. I saw already some problems which can be much faster solved with a normal computer, but in principle you can do simulations. But for the industry, I think quantum sensors will be, this is always a certain level in all the proposals. If you want to have money for quantum science, these are quantum sensors, because you have to measure something, then to feed it in a robot or in all kinds of things. So this is a big field for the industry also, but this was always the case already in the nanoscience area. So this is for me a continuation of the nanoscience area. And so my prediction is even the young students, I don't know, they will have a quantum computer at home. There may be some quantum computers, but it will not be like a laptop.
Okay.
Yeah.
I see Professor Halperin shaking his head.
No, I agree that I think quantum computer, no one is going to have a quantum computer
At home, no.
in their home. Assuming quantum computers are built and are useful, they are, the advantages of them that on very large scales, they can beat a classical computer. So that's not the scale in your wristwatch or in your iPhone. It's the scale of Google. So Google, for example, is interested. Why? Because they think maybe if they have a quantum computer, they'll have a more efficient, they can build a more efficient supercomputer to store information. It will facilitate data retrieval. Now that means, so what does it mean for you or for the students? Well, you'll have your little iPhone or whatever it is, and you want to find out some piece of information. You'll just as we do today. You're contacting a supercomputer out in California or whatever, or Nevada or near some power source, and you don't know it, but that's where the information is coming from. So you're going through the radio waves, and you will be using quantum. You may be using quantum computers without knowing it, but you're not going to be carrying it around in your head or in your wristwatch, or your robot isn't going to carry it around. There will be some big central ones that maybe will be useful.
Okay, so I want to go in that direction and talk about emergent behavior, right? So of course, one of the big intellectual problems of condensed matter physics is the quantum many-body problem. Do you believe quantum computers will solve the quantum many-body problem one day?
I don't think there is the quantum many-body problem. I mean, there are many contexts. There are many, you can have many. You can have electrons in a material. You can have. So will it solve some? Will it be useful for solving some quantum many-body problems? I don't know, maybe. I mean, yes, it'll be useful for solving some of them, but will it be solving the ones we're really interested in? I don't know.
Okay. So, Professor Haldane, what do you think about this? The question of emergent behavior and, the quantum computation and so on.
Well, emergent behavior, I guess, describes a lot of these new developments in materials that we've been seeing, that amazingly, you can store information in a hidden way in quantum systems. These are kind of behaviors that no one dreamt of until they first showed up in model calculations, and now people are actually building with qubits devices or virtual devices constructed in a strange way out of bringing qubits together and bringing them apart and connecting other qubits together to demonstrate some of these principles. Now, of course, we actually were hoping that we would use this to build these new qubits, which haven't arrived, but some of these principles I guess fractionalization is a key. One of the remarkable things which followed on from Klaus's discovery of the integer Hall effect was this fractional effect, where we found that the electrons which move around in metals, a normal description of materials is single electrons moving around, but sometimes those electrons in these exotic materials could split into a third of an electron or fractionalize in different ways, and then we found they can split in a very interesting way that leaves a kind of trail of entanglement between two half electrons. The amazing thing there is, if you study quantum mechanics for chemistry, you put electrons into orbitals and fill them up to build the atom. Well, what's been discovered now is you can actually have half an orbital, which is a very surprising idea. You can pull an orbital as a little box which can store an electron, and we can pull it into two half boxes, which leave a kind of trail of entanglement between the two of them. And if you put an electron into one side, it's also half in the other side. And then by having more than one of these things, by stirring them around and mixing up their entanglement trails, you can in principle process quantum information. So these are kind of very, very strange things that emerged from understanding that there were these new kinds of materials, and they've been a tremendous surprise each time they've emerged. And this is one of the hot topics today, I think, is trying to deal with these new ideas and new possibilities that have really emerged. No one really dreamt of the idea of a half an orbital, which is a Majorana zero mode, which people talk about.
That's right. So are we opening to the audience to ask questions? Because we're talking for quite some time. I'm sure there are people here who would like to ask questions. I see one hand up there.
Hi, Prof. Thanks for your sharing. And I'm a student from the CE school, and I got in touch with some quantum computings, which I feel very exciting because for me, based on my knowledge now, I think quantum computing or quantum mechanics maybe it's fundamentally probabilistic. That means you need to use the probabilistic to explain it. Otherwise, you cannot understand it. But I'm not sure whether my understanding is right or not. So I want to hear your understanding of the quantum mechanics or quantum computing based on several words to describe it. Thank you.
Okay, so it's a very generic question about quantum computers, right? So, of course, there is a whole evolution in quantum computation And you probably know there are several companies who are building quantum computers right now, right? But as we discuss here, there is going to be still some time before this becomes true. It's going to take a decade, maybe more, right? So maybe one related question for you guys is that, do you think there is a big evolution recently in this area?
Okay, it's fantastic to work in this field. It's a fascinating field, and I think for basic science, it's a fantastic area. But even today, we don't know the platform which will be successful in quantum computation. Today, we are using the squids established big, but you know, if you want to have really a working quantum computer, I was surprised to learn this from others, that you need millions, perhaps, of these qubits to scale it up. And you're fighting two exponential functions, I think, against each other. This engineering problem is exponentially difficult to scale it up, to solve something which gives the profit of an exponential better computer. So who will win? I don't know. But even today, we have not the platform. We don't know whether we have spin qubits in the future, whether we can use topological qubits. The cold atom physics is a very clean system, but to scale it up to a useful quantum computer, this will be a very, very difficult engineering problem then. But to work in this field, I think it's fantastic as a scientist. And if you like it, you should be enthusiastic about it. Yes.
Okay, any other questions from the audience?
Just a comment, I think, to make sure that we're on the same wavelength. So quantum computers do exist. There are quantum computers. They're just small, and they make a lot of mistakes, so they're not very good for anything. Well, there's arguments whether they have actually solved sub-problems that could not be solved with a classical computer. I think maybe they have, but they're not problems that anyone is particularly interested in. No one would spend $50 billion to get the answer to this problem. And there are many different types of quantum computers. Some of them use cold atoms that are moving around. Some of them use superconducting qubits, for example. And none of them work well enough for us to be able to say that if we were going to build a big quantum computer, this is the way to do it. So I think it's very exciting to try to build better qubits, because there are a lot of problems that we have to overcome, and we learn a lot about the world in trying to solve these problems. And as I think was hinted at, some of these problems, if you solve them, they also could be used for other purposes, like quantum sensors measuring things. So there's a lot of spin-off from this, and I'm all in favor of supporting the field with, as Professor Van Klitzing said, with the reservation that we not hype it to the extent that people are expecting they're going to see a quantum computer that's useful in the next 5 years or something like that. That's not, obviously. No.
I guess the question was asking also about probabilistic nature. And I guess one of the new emphasis and things is the measurement process itself, and using measurements to drive quantum states in interesting directions, things like quantum teleportation. And some of these new ideas, new realizations of quantum states partly involve assembling qubits together temporarily and bringing them in. This new quantum computer, which I guess a colleague of Bertrand's have been using, is a bit like at the cleaners or something. They bring all the suits out on a big line to bring them to you. The qubits are all numbered and on a racetrack, and they bring in qubit 131 and to connect it to qubit 93 and design a thing where it's not actually a physically local assemble of things, but these things last long enough, their stability, the information content is held long enough that you can move them around and bring them together in a plan. And using this, you can turn toy models of physical designs for quantum states into a sequence of things like this. And part of the thing you can do is you can drive the system into a state you want to get it into by doing a certain measurement, and depending on the outcome of that measurement, doing something else to the system. And so you're kind of gradually probing the system. I think this is probably the new developments is the exquisite control of quantum states. Before we were talking about a particle in a box dropping. Now we're playing kind of basketball with that particle in the box and swatting it around and getting it under control. And this is revealing these kind of new things we can do in controlling quantum states. And, these developments are occurring quite fast because people are developing. There's a, what is it, 1,000, let 1,000 flowers bloom or something. There's lots of different ideas for qubits and putting things together. And so many people are now working on this. Lots of interesting devices are coming up. And this was quite surprising that you could do these kind of measurement-based ways to push a state into exotic kind of things which possibly hold information. So it's an exciting time, I think. Yeah.
Thank you. More questions from the audience? Yep, someone there?
Thanks, Professor. I'm a PhD student in physics. I would like to ask a very naive question. As we know, the basic mathematical language for quantum mechanics is linear algebra. So assume that the dynamics of a physical system can be well described by something called Hamiltonian. It's a matrix. The following state can be transformed by the current state. So in my understanding, it's something just the first order approximation. In terms of Taylor expansion, we just preserve the first order. So it's like Newton mechanics. It's enough for classical system and the low energy situation. Do you believe that sometimes the error can come from the first order approximation, like the Hamiltonian matrix?
I'm not sure. The Hamiltonian is describing the evolution in time of a system. And actually what people are often doing now is actually moving away from a Hamiltonian description of systems to what are called quantum circuits, where you're modeling things and building qubit realizations of this, where the time evolution is not letting something just move, but a series of little kicks to it called unitary circuits. So you kind of, especially if you're building qubits, the time evolution is maybe not letting just things happen, but making things happen by doing a sequence of hitting it in a certain way, kind of like a way a regular computer works, in the sense it's always a digital computer is always a sequence of instructions, A, B, C, D. And so the Hamiltonian is the way you describe a physical object which is evolving in time, but modeling this by this discrete set of kicks is called quantum circuits. And there's a lot of work. People have moved often away from Hamiltonians into quantum circuits these days. Yeah.
Okay, thank you.
Okay.
A superconductor, as we all know, is a macroscopic quantum effect. I would like to know your views on the discovery of room temperature superconductors.
All right. Gentlemen, I'm the moderator, so.
So will it happen before or after quantum computers?
I think it'll happen before quantum computers, but so far at least the contentions for high temperature superconductors, which have been the highest ones that are claimed, at least, and I think people believe that at least some of them are very high, they're getting close to room temperature. but unfortunately they are at
High pressure.
at 2 million atmospheres pressure or something like that. So if you're asking me, will there be a practical room temperature superconductor, that may be after quantum computation. After all, you not only want it to be at atmospheric pressure. If it's to be useful, it has to have a high critical current. It has to have other properties. It has to you have to be able to build wires out of it. There's a lot of stuff a lot of properties you need, none of which are compatible with what I understand has been seen so far.
But life is full of surprises in physics, right? Who knows? I mean, if we knew how to make high-temperature superconductors, all the smart people out there would have gone and done it already, right? So anything like that, which seems unlikely, would have to come from a surprising discovery.
So we will have room temperature superconductivity before we have really, okay, all our energy by fusion energy and all our mathematical problems solved by quantum computation. I think then room temperature superconductivity has a better chance.
Yeah. Okay.
Thank you.
Thank you. Any more questions from the audience?
One over there.
Oh.
There's one.
A related question. So there's recent research on non-equilibrium processes, for instance, using attosecond lasers attosecond lasers that you can momentarily create room temperature superconductors. So what are your views about these non-equilibrium type of superconducting system? Using pulse lasers, they could actually temporarily create. They believe that
the question, if I understood the question, is there are experiments that claim to induce superconductivity by with pulse lasers, and you want to know, do we believe in it, or what is the question?
Whether these devices could be used for temporary superconductive devices, like maybe
whether it has a practical application.
Mm-hmm. I don't know.
I don't know. I haven't heard anything. It's a very interesting experiment, and if it's true, it helps us to understand superconductivity in a way that we didn't understand it before, but there's no direct application of it that I'm aware of.
Yeah, I guess there's certainly a lot more emphasis on non-equilibrium processes, quantum quenches and things. So the focus of a lot more focus on out of equilibrium systems, particularly in quantum studies. A lot of the people doing theoretical studies work with what are called quantum quenches, where you suddenly change a state. Where someone talked about the Hamiltonian, essentially you suddenly switch the Hamiltonian to something else. That was not really possible with solid state condensed matter materials, but now in cold atomic systems, where the systems are held together by laser beams in forming optical lattices, you can suddenly do these things where you suddenly switch the effective Hamiltonian and suddenly change the state. So there's a lot more work on these very non-equilibrium processes where you really suddenly do something and change things and see how something equilibrates or moves into a new state of equilibrium.
Thank you.
Hi, distinguished professors. I'm just a layman, so I just want to ask about what exactly can quantum computers simulate as compared to classical computers? Just a very basic question. And how and if so, do these two aspects need to be in sync to rather simulate something that neither of the constituent can simulate?
So what quantum computers can do that classical computers cannot?
Yeah, or like rather simulate instead of just
Well, the initial claim was that this algorithm that you could, that you could factorize large. Most of our cryptography is based on the idea that if you know a large number, if you know two large numbers and multiply them together and get an even larger number, it's very difficult to find out what two numbers will multiply together. But if two people each know one half of it, they can reconstruct things. So that all our cryptography is based on the idea that you can't. It's just too much work to factorize a number with 256 or 1,024 digits or hexadecimal digits in it. And it was, in principle, shown that a quantum computer could do that in a much quicker way, and that was initially the big thing that started a lot of this thing. The suggestion or the proof or whatever of Shor's algorithm that said you could do some of these things which just are too long to be done with a classical computer. The classical computer, the idea is the classical computer would just have to try every single way to do it till it found it. While the story about the quantum computer is it somehow checks out all the ways to do it at the same time, and an interference process leads you to the answer. So that was the starting point of proposal of something that a quantum computer could do that a classical computer couldn't do.
Okay, thank you. What about the idea of merging quantum computing with neuromorphic computing?
Well, I guess it's more likely that regular computing will be merged with whatever's happening in your brain before. There's nothing particularly quantum apparently about what's happening in your brain, although at least one of our colleagues is trying to investigate that. Yeah, who knows? Implants into your brain may be able to interpret what's happening on the individual level at some point. Maybe that's a horrible idea to think about.
I didn't think that was quite the question, but the question is merging the two kinds of computation together, and I think there's no question that if you were going to use a quantum computer, you need to have it run together with a classical computer to run the quantum computer. But also, before we get to these great big quantum computers that can factor large numbers, there have been proposals of trying to solve some simple chemical problems using them, and a lot of them do involve combinations of processes in which you compute something on a maybe a large classical computer, and then you have some problems that you need to solve with the quantum computer, and you go back and forth, and these are near-term. These are things that can be done with near-term computers. The quantum computer doesn't have to be so perfect. Maybe it makes some errors, but you can catch them. But you're using them in combination. So these hybrid computers are definitely, I think a lot of people are thinking about what could be done with them if we could only improve the quantum computers by only, let's say, making them only 1,000 times better than they are now, or 100 times, rather than making them 10 billion times better, which is what you might need for factoring a large number.
Thank you. I have one more question. So regarding, I'm not very sure. I've only briefly searched up about the magnetic tunneling junction effect, if I'm not wrong. Could you give a bit of insight into it, and if it, and more importantly, I would like to ask if there requires any form of electrical energy input into the computing, the magnetic quantum tunneling computing, and if purely magnetic flux could just use constructive and destructive interference to compute within magnetic flux logic gates, why is it necessary for advanced quantum materials? Yeah.
I got lost. There was such a long question.
No, I think you may know more about magnetic quantum computing than I do. Magnetic quantum tunneling, you said?
Yeah.
Magnetic quantum tunneling.
Yeah,
sorry.
it's just such a.
That
Yeah.
people do talk about. I'm not sure what you're referring to.
It was about something related to the magnetic domains.
Magnetic domains.
Yeah, and some magnetic. I'm not very sure. Yeah, so I'd like to just ask if any of you have any
So
inklings. Yeah.
People talk about using magnetic quantum junctions to couple spins and currents.
Yeah, spintronics, I think.
It's for spintronics.
Yeah.
I don't think it has anything to do with quantum computing.
Oh, really?
It certainly, it has to do with, no, so I think there are proposals for building memories that would be robust memories using this as a technique. And I think that's still under consideration, but there are a lot of competing techniques for building memories. But it doesn't have to do with it. Of course, in order to understand how they work, you need to understand quantum mechanics, but even just understand how an ordinary transistor works, you have to understand quantum mechanics. So in that sense, it's quantum mechanical, but it doesn't involve quantum coherence or the kinds of things that are very delicate. The quantum computers require being able to maintain quantum states in isolation so that you don't lose phase information. They're very sensitive, and this doesn't depend on that.
Thank you so much.
Thank you.
Hello. So thank you first for the interesting talk and the discussion. Oops. My question is a little bit off topic, but I got in a sense inspired by what Professor Halperin told. So it's about what you think about the future of academia in the very broad sense. So what I'm trying to say is that, all of these emergent behaviors in quantum mechanics and especially, quantum computation and stuff, they are very thrilling and fascinating. And apparently many people, looking at the audience, are interested in studying them. At the same time, what I understood, listening to the three of you, there is a little bit of a skepticism. You were talking about how those kind of quantum computers, they are still quite small. There are these kind of exponential problems, error confinement, I don't know, those kind of things to overcome. Oops. And at the same point, still getting back to what Professor Halperin said, he mentioned the fact that it's very important to this kind of research. It's a long life process of learning. So my question is, looking for my point of view, which is I'm in an early stage of my career, I feel that all of this pretty much not sustainable. So there are so many people working into this field. Your point of view are sort of skeptical. Quantum computation is a good thing, not so many people focusing on doing that. So many of us competing for it. Do you think that is something that academia can achieve in this current state? Where are we going, and then what are your opinion on the future of the scientific community?
So how you advise a young scientist on what to do with their lives?
You have to follow your passion, I guess, and there's certainly currently there's a large investment going on in this area, and things are certainly going to happen. What we actually get out of the developments, I'm not sure, but things are kind of, the qubits are getting better and better, surprisingly fast. And of course, that's partly a result of how much effort is being put into this. And for job prospects, I don't know. I mean, there's certainly lots of companies currently working in this area, and certainly I think a training in physics is a helpful training in all kinds of different ways that your career will go. You don't know what's going to happen in the future, right? And I would say, you know, do what you're to get into basic research. I think you need your own passion to carry you forward and follow your dream as far as it can go. And not everyone is going to end up in a basic research lab. They're going to end up in industry in other places. But I think the training you get in thinking in physics type or generally scientific things will be a good basis for whatever happens in the rest of your life, I think.
Well, I would agree that my advice would also be follow your passion, and the passion you should have if you want to go into this field, it should be that, one, you really want to understand how the world works, and that it's a passion to try to understand how the world works. You have to like mathematics. If you want to be a theorist, particularly, you need to see beauty in mathematics and seeing a mathematical explanation for things. And studying quantum mechanics and applying quantum mechanics will satisfy that and will prepare you, if not for doing quantum mechanics for the rest of your life, for other things. Again, if you want to be an experimental physicist, you also have to have a love of obviously trying to discover how the world works. You also have to have a love of mathematics, but in addition, you have to love to build things. You could probably better describe the skills that are necessary to be good with your hands or with your mind, to think creatively about how to solve problems and get a thrill out of solving problems and finding new ways to measure things. And if that's your passion, then follow it. And I think that this is a good field where you can do it, and you can probably, as the job prospects, I think, are reasonably good. I mean, you have to know what to compare it with, but I think they're reasonably good, that you will get some kind of employment that will use these skills, and that you'll be happy that you studied it.
Professor von Klitzing, you have something to say?
I have the best position as a Max Planck director because this is very important. I'm always fighting for the freedom of science, that we have not the top-down organization of what you have to do. And in basic science, you never know where you have a hard wall, in which direction you need the freedom to optimize your way. I think this is a fantastic situation at the Max Planck Institute. If you look at the Nobel Prize winners, every year a Nobel Prize winner at the Max Planck Institutes, because they have the freedom to optimize the way and not to promise what you have to do, deliver in 5 years' time. And if there are politicians here, so I recommend always to give the responsibilities then to the scientists and not to the top-down politicians. Okay, we are always happy to apply our things, but to have breakthroughs in science, you need the flexibility. And so that's my hope. But then the scientists should be also responsible. And therefore, I'm enthusiastic about quantum science, but I was a little bit warning that the fear that some enemy will crack the code, and therefore we have to make some Manhattan projects in quantum computation. Whether this is the best way to support science, I'm skeptical. And therefore I was a little bit careful that we have this hype a little bit, which is driven by the fear. It was mentioned that the Shor algorithm started this hype. And we have so many fantastic other problems to solve. And as a scientist, I know there's a certain the amount of money is constant in a certain way also for the science, and therefore we should optimize it, and then the scientist takes the responsibilities in which direction it's really useful to spend the money, but then to give them responsibilities. This is very important. If you're responsible, then you are careful also in your spending your money, yes? Otherwise, if you have a big project and there's a lot of money somewhere, you try to get this money, and very often not the best scientists then are successful to get receiving this money. So that's my wish always, that we keep, at least for basic science, this freedom. And but there are so many, and 80% of my students go to industry and solve problems. And there should be always a balance, but should not have 100% basic science. And I'm always satisfied if I see the application of my basic research. And as I mentioned, this was my highlight, that after 30 years of the quantum Hall effect, we have this big application in metrology, yes, and it's worldwide accepted. And so this is a success story. And not everyone has the luck to be the Max Planck director, yes.
Very true. So I have some questions from people online. One is, how should I get started to learn quantum skills? Quantum skills related to life science research. Thank you. So how do you learn quantum skills?
Take a course in quantum mechanics.
There's a question.
The answer was take a course in quantum mechanics.
Maybe you open a book on quantum mechanics and start studying it, yeah?
Better take a good course.
And
have other students to study with and ask questions. Studying it in a group
is much better.
But as for application to life science, that's another matter. But for sensors, certainly there may be some applications to sensors. NMR, magnetic resonance imaging, is a big application, if you wish, of quantum mechanics to medical science, and so there are many such applications. Certainly magnetic resonance of various kinds are used for deciphering proteins, and so there are a lot of applications, not of quantum computing, but of, that you need quantum mechanics to understand not the biological processes themselves necessarily, but to understand how to build machines that will help you build better drugs or whatever, or diagnose diseases.
So in that direction, so what do you think of the concept of quantum engineering? Because I've heard this concept several different places. A person says, I'm a quantum engineer. Does that make sense to you?
Well, someone working on building quantum devices.
So a quantum engineer is someone who builds quantum devices. So any student in a lab is a quantum engineer.
Well, quite a lot of, I guess, in electrical engineering departments, there's now a larger emphasis on quantum engineering or quantum science, and this really involves trying to build practical qubits as opposed to trying to think about the materials you might use. Or
I met different people in the industry which are producing quantum computers. The bottleneck is quantum engineers today, and this is perhaps in the future will be a new direction, that you are familiar with all this technology, with microwave technology today, with all the, if you stay with squids, the low temperature, you go to very, very low temperatures. I never believed that something will be used at such low temperature in practical applications. For a long time, normal computers, IBM had the idea 20 years ago to go to low temperature. No, low temperature is not acceptable for industry. Now we speak about millikelvin temperatures for quantum computation. It's unbelievable, but there's a new education for the engineers to work in this direction. But as long as we don't know the platform where we will develop really a big market, then you need fundamental education in all kinds of quantum physics and quantum science.
Okay.
If you're trying to build a better laser, that's quantum engineering. If you're trying to build a better computer chip, that's quantum engineering.
And sensor devices, yeah.
Makes sense. Any other questions from the audience? Yes, please. Oh.
Hi, Professor, and thank you for your talk. I am a student in mechanical engineering, and so my question is non-professional. I want to know what leads you to this area, the quantum physics, and did you meet any obstacles or difficulties during your research? And finally, what leads you to the Nobel Prize? I don't want to win a Nobel Prize. I know there's no Nobel Prize for engineering, but it's interesting because you mentioned the passion, but I don't know, what's your passion on your area or on your research? Thank you.
Well, I think everyone who goes into basic research ends up doing it because they have a passion. Now, one always gets asked this question, how do you get a Nobel Prize, right? And of course, the answer is luck. But you have to be prepared. I mean, basically, I think anyone doing basic research has got some chance of getting...
Take it, yes.
Got some...
No kidding. I don't believe this.
I say anyone doing basic research has some chance, incredibly tiny, of getting a Nobel Prize, and that's because most of the most amazing discoveries are things that no one dreamt were out there. Now, if people knew something was out there to be discovered, most of the time the really smart people would have gone and done it already. So the most amazing discoveries are things that no one, including the people who find them, expected. And so there's a lot of luck. You go for a walk in science. Your career, the things you're interested in takes you on a kind of random walk from one to another. And maybe you're walking along a path, kicking up the dust. And if you're not looking at your feet, you might not notice that you've unearthed a huge diamond and you'll walk on by, right? So often something slightly unusual may emerge in your research. And if you've got a completely focused drive that you have to meet some project and finish it, you might say, I don't have the time to investigate that. But some of these unusual things that you might come across in your research or your activities will most likely be something slightly interesting, but very occasionally there'll be something that no one ever thought was there, and that's how some of the most interesting discoveries get made. I mean, Klaus here never dreamt he'd see the quantum Hall effect, and people had done similar experiments in a slightly different way, which wouldn't have exposed them to being able to see what he found, but he found this unexpected, remarkable thing, but he was prepared enough to recognize, wait a minute, that's incredible. Why do I get the same answer in 2 different experiments, up to 4 significant figures or something, right? So something strange may emerge, and very, very occasionally, that's just something that no one ever dreamt was out there, and I think there are lots of things that we believe are true, and we have kind of confused ideas about, and suddenly new things will emerge from science, from observation probably, that show us that there is new things. And that's actually part of the history of what's made quantum science so exciting in the last period. Lots of things which are unexpected things really have emerged, and I guess that's the emergent structure. So that's my answer anyway.
For me, it was very helpful that we have the technology really to play around with quantum phenomena. So I mentioned that we have controlled single layers of atoms of different materials, and then we can predict that we change the properties. So all our world consists only of these 100 atoms, these building blocks, and just by arranging this in a different way and controlling them, then the scanning tunneling microscope and all these microscopic equipment which can control at the atomic level, then automatically quantum science can be applied and you can see the result. So when I started 60 years ago, I never believed that particle in a box will be something like only an educational test that quantum mechanics can produce some energy levels. But today, all the lasers, all the illumination, everything is based on this knowledge. And then you can really control this in the lab as an experimentalist. It's fantastic to see that quantum mechanics works so well, yes.
Thank you for your answer. And can I take a closer look to the metal?
Yes. No, there's two of them. The name is different.
It's very rare. All right. I have to say, this is fun. Anybody else?
Science is fun. Yes.
Maybe later. Sit down. Sit down. Sit down. We have a question, right? Oh man, that's what happens. Okay, I think we have a serious question there, right? Okay.
Sorry for waiting, and thank you, professors. So my question is, I would like to ask your opinion about the relation, the role of information in the description of physical phenomena. So on the one extreme, I could say that information is so fundamental that even some of the physical laws can be described in terms of laws of information. On the other end, I could claim that information is something we made up. We make up a concept, we invent it so that we can apply the physical laws to make better stuff, make quantum computers. So what is your opinion about this?
All right.
Well, information is, I guess, people talk about flow of information is what we know about a state by measuring it, I guess, yeah, there's a lot of emphasis on how fast information can flow, right? Before people would talk about how energy flows, right? Now it's realized that information, in the sense that you did something to the knowledge or whatever that you did something to a system at a certain point is information, and then that will, for example, you have a magnetic system and you flip a spin at point X, you know you flipped it at time 0, and the information that was done will spread, and there's a lot of discussion and trying to formulate how information flows to understand quantum dynamics, and there's some reinterpretation in this as a flow of information.
Do you see any practical applications of quantum information?
Well, the whole quantum computing idea is the processing of quantum, I guess, information processing by quantum mechanics.
Right.
So what was the question? Quantum?
No, I'm just
practical.
Is there a practical use to quantum information? Or it's too early to ask this question?
You want to distinguish quantum information from classical information?
No, we're not, yeah. Well,
practical use of flow of information, anytime you look at your watch or whatever, of course, this flow of information is at the heart
flow of
of
information.
everything that's going on in computers and today, but whether the additional quantum information part, the unique quantum part, that's not clear. Well, I'm sure at some level it's important, but it's happening whether we understand it or not. So,
I mean, I guess decoherence is viewed as the loss of information, right?
Right.
That you've stored information. If you have information about a quantum state, the information is I put it into a definite state and I know how I prepared it, and possibly I'm manipulating it to do some computation. The loss of quantum information would come about through the entanglement with the environment, and one views that as the spreading of the information, which in some sense is the loss of the local. So there's a lot of, certainly it's conceptually become quite an important part of the field to think about information flow. And I mean, even our string theory colleagues have moved into they wish to reinterpret space-time as quantum entanglement and information.
Yeah, exactly.
I guess there's no, since string theory has run out of any, so far it's run into some kind of impasse at the moment. They're now reformulating, the string theorists are now even talking about quantum information. Yeah.
Any other questions, folks? Well, we're coming almost to the end, right? So we just have a few minutes left. You want to ask? Okay. So go to the microphone, or someone take a microphone to him.
Professors, thanks for your talk. And I'd like to ask a relaxing and a specific question. Could you share one most unforgettable memories in your science past or career, and something like your feelings or your opinions about it?
Is there a moment, an unforgettable moment in your career?
Well, he certainly has one.
Yes,
At least one.
I told you, I attended hundreds of conferences, but this conference of the META convention, which coordinates in the world all the measurement system. So in 1889, we introduced the meter standard, the kilogram, and this. And at this time, from this time, we have this international conference that all the countries come together to agree that we have international trade, that not each country has another measurement system. And then this change in this international system of units, the base units, I was invited to convince then these delegates from all over the world to think about that fundamental constants is the most stable thing we can have for international trade. And that all the countries agreed on this. This was, for me, the most emotional moment.
And it was his work.
Yeah, this really, and this by accident, I just have done basic science on a microchip to understand how can we make a transistor faster, how can we miniaturize it. So it was normal modern semiconductor physics, yes, and then have the chance to see something unexpected. And this has 30 years or 40 years afterwards, this big influence on our worldwide international system, and to have our own constant, which will live forever, that's highlight in the life of a scientist. Yes. So, but okay, not everyone has a chance.
Yeah.
There's only two scientists, living scientists, which have their own constant. So Brian Josephson, superconductor, and I'm in semiconductor physics. So, and both have this application in fundamental constants. Yes, and this is a fantastic field. Now you can ask interesting question about fundamental constants, but this is an extra lecture. And
Yeah.
but this was for me the highlight.
Duncan.
The Nobel Prize was nothing against
Yeah. So, yeah, I guess, I mean, occasionally one finds something surprising, and I was certainly surprised when I discovered that what people thought was the way some magnetic systems worked was completely incorrect. I was shocked. But again, I stumbled across something because I was viewing it from a different viewpoint from most of the rest of that field. And occasionally you find out, as I say, we'll find out that things that people believe are true and we teach our students are true, and suddenly something will change. Someone will find that we actually fooled ourselves, right? So I stumbled on such a thing, and I was quite shocked at the time. But anyone who's found something unexpected, I think, will have the same kind of surprise in their scientific career if they actually stumble across something like that.
Professor? Yeah, well, I certainly have not had any singular event such as my distinguished colleagues have had. But for me, numerous small events, I would say, were very exciting at the time to explain some experiment that seemed completely unintelligible, and then suddenly you understand it. In some cases, I can think of some experiments that weren't very important. I don't think anyone has thought about them. In other cases, a discovery has had ramifications. At the time, I didn't know which one was going to be more exciting. When in my PhD thesis, the first problem I solved was a one-dimensional problem. I was able to exactly solve some one-dimensional problem, which I don't think had any particular importance, but suddenly, realizing that I could solve this problem that seemed very hard to solve, and I was able to use the math I had learned in my course at Berkeley and whatever, and suddenly it all came together. It was my first real discovery. It was very exciting. Now, maybe not the most important thing, but okay, that's what motivated me and continues to motivate me. It's part of the lifelong learning, lifelong discovery, hoping to discover new things, maybe little things, maybe big things. But you don't know necessarily what's going to turn out to be important.
Understanding something that wasn't understood before is an incredibly satisfying thing. And you realize it comes together and it works.
Follow your passion.
Exactly, follow your passion.
Thank you very much.
All right. One last question.
Thank you for your great talk. I'm a PhD student at computer science, and I'm working on artificial intelligence. I remember you also mentioned the connection between quantum physics and artificial intelligence. So I'm curious, how it will influence existing AI, and how AI may influence quantum physics.
Well, people are trying to use AI to model quantum states, which are quantum states of matter can be very complicated, and some people are hoping to use AI techniques to represent the essence of certain quantum states. So people that are trying to use AI techniques in all kinds of areas, but also in quantum physics and things. It's a new tool. It seems to be very useful all over the place, and essentially to try to get a simpler representation of very complicated states is one thing. People are hoping to use AI for in at least condensed matter quantum research.
I think there certainly have been many applications already of people who've used AI to solve quantum problems in quantum mechanics, to write they find it's useful to write programs, maybe to write articles, or true articles, false articles. Anyway, it's certainly useful as a tool. Now, if you ask the other way, will quantum computing ever be useful for
No.
artificial intelligence, that's another matter. But that that artificial intelligence will be useful in solving quantum mechanical problems is no question.
Okay, do you want to ask a question? You're going to be the last of the last.
So sorry, because I know this is a very rare opportunity, I would just like to ask. Thank you very much for your sharing today. I'm currently a year 1 student doing physics in NTU, and I would just like to ask a question that I don't think a lot of people can answer, but I would like to know from your own perspective, like what advice can you give or what understanding do you have? So I believe strongly that quantum mechanics is going to bring humans very far in our understanding about the fundamental nature of the universe. And I believe that most physicists and aspiring physicists make the choice to go into science with a very simple and powerful motivation to discover this fundamental nature. And especially in the field of theoretical quantum mechanics, it takes a lot of courage to be able to go into this area of research, knowing how much uncertainty that physicists have to deal with. So I would just like to ask, given how small humans are within the scale of the entire universe, even if one day we do discover a unified theory of how the universe works, in what way would this knowledge have an impact on humans' role in the universe? And in other words, what do you think we can do with this knowledge?
Wow. What a last question.
Wow.
We want to know.
Let's start again, okay.
We want to. I guess all science is, and fundamental science is trying to understand the world around us. And our view of the universe, it changes, right? I mean, we didn't know about dark energy 15 years ago or whatever. So who knows what, people are trying to do, understand gravity and try to quantum gravity and involve quantum mechanics. Who knows where these things are? But we're all driven by just trying to understand the world. And probably in small steps that we can individually take. And humanity, I guess, has been doing that ever since they learned how to talk, I suppose.
Well said.
And we have always more questions than answers. So if you have no new knowledge, then you can build up on this knowledge. And I have the experience, I have always more questions than answers. If I found something, then you can build up on this basis and then to understand more. I think this is a driving force for all scientists, yes, to understand our world. We don't know. And Nobel Prize winners, they have the same knowledge as the normal people here. So you ask us questions where we perhaps also not competent. We just want to learn more. So continuous learning, that is also for us very important, yes.
But in science, the big thing is actually not to find the answer, but to find the right question.
So it is the journey of curiosity that is more important.
Yeah.
Thank you.
Thank you very much. Okay, folks, I want to thank the distinguished panelists for being here and having this great time with us, and all of you who came here today to listen to them. Thank you so much. Have a great night.
Let's put our hands together to thank the professors. May I request the panelists to remain on stage and all audience members to remain seated until the end of the event for a photo-taking session with everyone. May I now invite Professor Fan on stage to present the mementos to our distinguished panelists.
Give us a memento and a picture. We get some plaque.
Thank you, Professor Fan and our distinguished panelists. I would like to request the professors to remain on stage. May I remind the audience seated while I invite the following guests on stage to join the group photo taking. His Excellency Dr. Norbert Riedel, Professor Castro Neto, Professor Sam Si Chin, and Nanyang Assistant Professor Yang Bo. Thank you, professors and distinguished guests. I invite you to please take your seat. Now let's have a group photo together with everyone in this lecture theatre. This brings us to the end of the panel discussion with Nobel laureates and eminent scientists.